So just a quick review here of Compton scattering or the Compton effect. It's very similar to the photoelectric effect. It involves photons striking something, atoms, and it involves electrons within the atoms being liberated from the atoms, being kicked out of the atoms somehow. But the difference is that in the photoelectric effect, those photons, when they strike the atom or they strike the electron, the photon is absorbed entirely in the photoelectric effect. Whereas in Compton scattering or the Compton effect, the photon isn't absorbed, it kind of clips the electron. It kind of glances off of it. And that will happen as opposed to the photon being absorbed if the electron that the photon makes contact with is a free electron. So if the electron is actually bound to an atom, the photoelectric effect is the only thing that could happen. Well, unless the photon doesn't have enough energy to remove the electron. But the only way a photon can ever lose part of its energy is if it interacts with an electron that's already free. During the collision between the photon and the electron, energy is conserved. We'll also learn today that momentum is conserved. And the most significant aspect from yesterday's class, other than the conservation of energy during the Compton effect, is that this is telling us photons have momentum. And it leads us, I'll just go right to the formulas, it leads us to, on the top part of the screen here, the formula on the left and the formula right after it. Actually, my mistake, the formula in the middle and the formula on the right. So these two formulas here, this one and this one, are new formulas as of yesterday, and they are how you find the momentum, or how you can find the momentum of a photon. I also have your energy formula for photons up there, and then for particles with mass, like electrons or alpha particles or neutrons or protons, there are two formulas, one for energy and one for momentum. This is a visual of what's going on during the Compton effect. So you can see that the wavelength of the scattered X-rays are longer. It's a longer wavelength. That makes sense because if the X-rays lose energy, if the photons lose energy, they have to have a longer wavelength. Greater wavelength afterwards, which is shown over here, greater wavelength afterwards means less energy afterwards. This is the initial kind of diagram of what's going on. If energy is conserved, then this is the bottom line here. And this is where we left off with the final example yesterday. The energy of the incident photon, that means the photon that's about to hit the electron, is going to be more than the energy of the scattered photon. The scattered photon is the photon afterwards, because the photon loses energy. And whatever energy it lost, it has to go into the kinetic energy of the electron. There's no work function involved here. So all that being said, does anybody have any questions you would like me to go over from that problem set? Go ahead. Number 6. We want the momentum of a 4 million electron volt photon. The nice thing is we actually have a formula here which relates energy of a photon to its momentum, to the magnitude of the momentum. And I kind of alluded to this yesterday, but I'll be very specific here. In these formulas under quantum mechanics and nuclear physics, where you find the momentum of a photon formula, or formulas, the momentum is just the magnitude of the momentum. It's not a vector in these formulas. We're going to take that into account when we need to. The only thing is that this is a formula that requires standard units, which means we need to have joules going in here. Speed of light has to be in meters per second. Momentum has to be in either Newton seconds or kilogram meter per second. So this energy up here is not in joules. It's 4 multiplied by 10 to the 6 electron volts. I feel as though the last couple of times we've talked about converting electron volts to joules, I haven't been doing that great of a job. So if you want to know what this is in joules, you can either set up a ratio, which I will show you in a second, or what you can do is multiply by the number of joules per electron volt. Looking at the units, electron volts times joules per electron volt would result in the electron volts canceling and being left with joules. And we know there is 1 electron volt in 1.6 times 10 to the negative 19 joules. So that's why we're going to multiply. If that doesn't make sense to you, then you can always set up a ratio. 1 electron volt is 1.6 times 10 to the negative 19 joules equals, we had 4 million electron volts over x joules. In either case, what you're going to get here, if my math is right, is 6.4 multiplied by 10 to the negative 13 joules, I think. Now we can use that formula in the top left of your screen. We can put the energy, 6.4 times 10 to the negative 13 joules equals the momentum times the speed of light, which is 3 times 10 to the 8 meters per second. Now is not the time to start getting into why the units are going to give you the units of momentum. It's not important. But when you divide this number by that number and get, 2.13 repeating maybe, you get 2.13 repeating times 10. I believe it's going to be times 10 to the negative 21. This is our answer. So everything is good then. You just entered something wrong. Okay. And that's probably, for a person like you, if that's happened before, or anybody else where it has happened before, that's probably your troubleshooting when you're writing an exam and you have multiple choice and you're not getting the right answer. It's not to start panicking going, I don't know what I'm doing. It's to go, wait a minute, I know what I'm doing. Let's just double check the numbers. Does anybody have any other questions? Go ahead, Liam. 9? So we want to compare the momentum of a photon with a particular energy to the momentum of an alpha particle with a particular energy. This is a not difficult, it requires a lot of organization, because first of all, you're comparing the momentum of a photon to the momentum of a particle. When I started talking about these formulas at the beginning here before we got going with this, I tried to make an impression on you that the formulas at the top are reserved exclusively for photons. The ones on the bottom are reserved for particles with mass. That will change on either tomorrow or Thursday. One of these formulas, it turns out we can use for both, but for the time being, we won't worry about that. The other thing I want to say about number 9 is when you are asked to compare one thing to another, we always want to calculate that thing divided by the other. The analogy I've used before is if you're 18 and I'm 54, and I say, how does my age compare to your age? You take 54 divided by 18 and you say, Mr. Way is 3 times as old as I am. So what we really want to know here is the momentum of the photon, the magnitude of the momentum of the photon over the magnitude of the momentum of the alpha particle. So how do we calculate the momentum of a photon? It's h over lambda, or, well, you know what? We can use E equals PC, and I can save a lot of my explanation here by saying we can find this momentum by doing everything we did with Ben's question. Question? You're what? Does anybody else want me to continue? Maybe just take a few more steps. The reason why subtracting is not a good way to compare in science anyway. When you subtract things that are outside of the science classroom or the lab, sometimes you get a meaningful answer. Like, what's 54 minus 18? 36? Help me out here on that. 36. So, is it meaningful for you to say Mr. Way is 36 years older than I am? Yeah, that makes sense. But when you're dealing with numbers that I'll just give you an example. Let's say that you calculate the value of something in physics and you get 1.2, which might be the energy of a photon of visible light. And then you have the energy of a photon of X-ray radiation, and it is that many eV. And I ask you to compare them. A more meaningful comparison would be to divide, because the big one is so many times bigger. And I'll take this to an extreme. What if we had a radio wave photon? I don't even know what that would be. I'm just going to say -5 eV. What if we had a radio wave photon? If you take 12 or 14,200 and you subtract that number, your calculator is basically going to say 14,200. I mean, it will say 14,199.9999, and it starts to lose the meaning. By the way, I don't know if that's a radio wave photon, and it's going to bother me unless I check it out. If we had that energy, and I set that equal to hc over lambda, I'm just taking a detour because I'm saying, and it's being recorded, people might watch this, I'm saying it's a radio wave photon. I don't know. Let's check it out. I don't want a student who's absent looking at that later and getting a misconception about something. Lambda would be hc, 4.14. I don't know where the t came from. That's weird. 4.14 multiplied by 10 to the negative 15 times the speed of light, divided by that energy, 1.2 times 10 to the negative 5. Let's see, hc over E equals lambda. Okay, so it's not a radio wave photon. It's probably a microwave photon. But microwave radio, they kind of start to blend together. It's microwave or radar. It's 10 centimeters. So anyway, you get my point there? Okay, going back to this question, in order for you to find the momentum of the photon, you need to know the energy of the photon that you are told, 19.6 eV, which, by the way, is more than visible light. It's probably ultraviolet. I wouldn't say it's X-ray. If I take 19.6, sorry, I got lost in my thought there. I was going to say maybe we should work in eV, but I'll explain to you later why we can't. So if I take the number of electron volts times that many joules per electron volt, this is the energy in joules of that photon, everyone. So if I divide that energy by the speed of light by using the formula on the right side of your screen, I get this momentum. So 1.045 times 10 to the negative 26. That would be Newton seconds. By the way, our whole discussion here of, what's the best way to compare, on an exam, it wouldn't be open-ended like that. It would say very specifically, what is the ratio of the momentum of the photon to the momentum of the alpha particle? Now, in order for us to find the momentum of the alpha particle, we have to use this traditional momentum formula, but we don't know the speed. However, we can use Ek equals a half mv squared to find the speed of the alpha particle, to find the momentum, to find the ratio. However, again, this formula right here only works with standard units. So the energy of the alpha particle is 0.125 eV. We have to do the same conversion, convert it into joules so we can work with it. And if I multiply by the number of joules in a single electron volt, this is the energy in joules, which I can use this bottom formula with that energy and the mass to find the speed. Alpha particle, it's been a long time, times 2 divided by the mass of an alpha particle, 6.65 times 10 to the negative 27. I need to take the square root now. What I'm looking at right now is the speed of the alpha particle, pretty lazy alpha particle. It's not moving that fast. I mean, that's fast, but for an alpha particle, not. I want to now multiply by the mass of the alpha particle to get the momentum. Again, you know, with a photon, just to take a break here, with a photon we have this formula where you can go energy to momentum, momentum to energy. We just don't have a single formula for particles with mass. You've got to do that intermediate thing by finding the speed. So this is the momentum, 1.63 times 10 to the negative 23. And I'm assuming that if you take those two numbers and divide them, you get 6.41 times 10 to the negative 4. All right, we're going to move on and take a look at the second part of the Compton effect. This is on page 56 of your unit handout. I know that at the top of page 56 it says the Compton effect part 1. That's a typing mistake. It should say part 2. And we're going to continue to use conservation laws today. Some of the problems that were assigned are like a couple of the examples we did yesterday that involved conservation of energy. Today we're going to use conservation of momentum. We're also going to use something called the Compton scattering formula. So the examples continued. It's the same setup as the previous example that we finished yesterday's lesson off with, where you have photons of wavelength 0.24 nanometers. They are Compton scattered. What does that mean? It means they strike free electrons and they're scattered at a particular angle. The X-rays happen to be scattered at 85 degrees, and the electrons happen to be scattered with a particular speed at a particular angle. And it says use conservation of momentum, which, you know, I'll be honest with you, that's a real pain because momentum is a vector. You can't just say momentum before equals momentum after plus momentum after. You have to use a vector diagram or some other strategy. So use conservation of momentum to determine the wavelength of the photon. And we used conservation of energy yesterday and determined the wavelength of the photon as 0.2422 nanometers. That's the answer from yesterday. It says do not use the measured angle of the scattered photon. That's going to be there for another question that we'll ask, 2C. So how do you solve this kind of problem where you have information about the photon that's moving, and you're going to have to, over the next 10-15 minutes, write all this down. But here's a picture of the before and after kind of put together. Okay. So we have the photon, which is moving, I'm going to say to the left, although it could be moving in any other direction. And we have the electron, which I'm going to say is scattered up, and we have the photon that's scattered down. And we're going to label some information in this diagram. We need some information here. So let's start with that. This is going to be the building block for your two-dimensional collision analysis. This is what we did in Unit 1. Except it wasn't a photon and it wasn't an electron, it was a pool ball and another pool ball. Notice that when I drew the scattered photon, its wavelength is noticeably larger, although we learned yesterday that the actual increase in the wavelength is not that significant. All right, so in order for us to analyze conservation of momentum, you need to calculate the momentum of the things that you know enough information about. What do I mean by that? I mean that you know the wavelength of the photon before, and that's enough for you to calculate the momentum of the photon before. You know the speed of the electron before, so you should be able to calculate. I hope it's not going to take you very long to do this one. You should be able to calculate the momentum of the electron before. And you should be able to calculate the magnitude of the momentum of the electron after. So these arrows are just showing the direction of the momenta. But your next step is going to be to calculate the momentum of the photon before and to calculate the momentum of the electron before and to calculate the momentum of the electron after. You need to calculate these three things for me. And I've already done all these calculations, so I'm not going to be plunking away on my calculator. I want you to do the work today, and then I'll bring up the numbers, and we'll see, hopefully, that everybody's numbers match mine. And if you're watching this as a video, I'm not editing this and cutting out these dead spots where everybody's working. If you're watching this, you should be doing the calculations as well. Just to note that the momentum of a photon being h over lambda only works in standard units. So you would have to convert those nanometers to meters. And I think the most efficient way to do that is that when you type in that wavelength, you just type 0.24 times 10 to the negative 9, because that's what nano means. It's the most direct way to do it. So Tyson, have you got the momentum of the photon before? Can you get that number for me? Can you say that again, please? I got 2.76 times 10 to the negative 24. So what we're doing here, I'll just take a break from this screen, is we're using this formula. Are you good now? Okay, but maybe I'll just show just in case. We're taking Planck's constant in standard units, 6.63 multiplied by 10 to the negative 34, and we're dividing by the wavelength. I can't expect you to be able to convert 0.24 nanometers to meters in your head. So again, I think the best thing to do is just go 0.24 times 10 to the negative 9. And this is where I'm getting that number from. Amanda, what is the momentum of the electron before? It is 0. It's not moving, right? I mean, we can talk about the drift velocity of the electron, and it might kind of be moving from one atom to another, but we essentially say that it is moving so slow that the energy that it has is not important. So it has no momentum. And then the momentum of the electron afterwards, Arden, do you have a number for us? So we would take the mass of the electron times the speed of the electron. And there's that distinction, everybody, while we're just waiting for Arden to get a number for us, where we have P equals h over lambda for a photon, but we have P equals mv for a particle with mass. Arden, did you in fact get 3.7 times 10 to the negative 24? Okay, so those are the momenta we know. Now, where we're going with this is if you want to find the wavelength of the photon afterwards, you need to know its momentum. If you knew the momentum of the photon afterwards, then you could set it equal to h over lambda and find the wavelength. You cannot find the momentum of the photon afterwards by just taking the momentum of the photon before and subtracting the momentum of the electron. It doesn't work that way, because we could do that with energy, because energy is a scalar. Vectors don't add up or subtract that way. So my best advice to you, and we're getting near the end of the course, like, well, not really close, but we're almost done the third of 4 units. You have to know how to do two-dimensional collisions and the analyses in 2 dimensions on the diploma exam. And I think the best strategy is always to think X and Y. Is to now look at each of these momenta. There's 3 momenta that you're looking at on the screen, and determine the X and Y component of each. So briefly, and then I'll give you a couple of minutes to do so, the X and Y components of the momentum of the photon before, that would be this X and this Y component before, should not require much thought. They won't certainly require any calculations. Requiring even less thought and 0 calculations would be determining the X and Y components of the electron before. Requiring a small level of trigonometry, we would need to use the hypotenuse here, and the hypotenuse of our vector diagram is the momentum that the electron has, and a right triangle would allow us to find with the angle the X and Y components. So no calculations, no calculations, a little bit of thought, and then up there you're going to have to do a couple of calculations. Remember, the X is horizontal, the Y is vertical. I think it's pretty obvious that since the way we've set it up anyway, with the photon traveling to the right, which is wise, why would you start to say the photon is traveling 20 degrees north of east? That doesn't really, it's not a good problem-solving strategy. Since it's moving entirely to the right, all of the momentum is X and 0 is Y. Since the electron before it's struck by the photon is not moving, it has no momentum, so it has no X and no Y. And then, of course, for the other electron, not the other electron, the same electron afterwards, its momentum in the horizontal direction would be the hypotenuse momentum, the actual magnitude of the momentum, multiplied by the cosine of 47.22. And then if you instead multiply by the sine of 47.22, you would get the vertical. I want to take a little break from our discussion here of the Compton effect and just say to you, it isn't always cosine gives you X and sine gives you Y. It will be, though, in this case, because the angle that you're told gives us an adjacent side that's equal to the X. But if the angle were given between the vertical and the vector, the adjacent side would give you Y. So you want to be very careful with that. Anyway, can I get a yay or a nay on those 2 numbers? Looking good. So now how do we put this all together? Well, what you need to do now, and I haven't shown any real work here, but you need to somehow determine the X and the Y for the other vector. And the key is, everybody, that the X's I am going to highlight in yellow, on the left have to add up to the x's I highlight in yellow on the right. Momentum is conserved in the horizontal direction or dimension. So, in my mind, I'm looking at this one here on the left, which is 2.8 times 10 to the negative 24. This one's only 2.5 times 10 to the negative 24. So we're literally going to subtract those because they're in the same direction. We don't have to take direction into account. If you were looking for what we're going to do here, and I'm going to write this down and then erase it. What you would be doing, I won't erase it, is you would say that the x before, which is 2.7625 times 10 to the negative 24, plus 0 has to be equal to, so there's the 2 highlighted on the left, 2.52 times 10, I'll put the decimals, 2.5238394 plus this x of the photon. While I'm at this stage, we can do the same thing for y. For y, this is our x. For y, we're going to have 0 plus 0 equals 2.72739858 multiplied by 10 to the negative 24. And I just realized that I didn't write times 10 to the negative 24 in my x equation up here, so I'd better put that in. But in the second equation, it will be plus our y component. So just to really bring things home and make sure everything's complete, this is a statement of my conservation of x. If I look at the y components, this 0 plus this 0 has to give this y plus this y, and that's what the second equation is. So I'm literally saying x before equals x after, y before equals y after. When you look at the highlighted blue equation at the bottom of the screen, I hope it's clear that when you solve for y, you're going to have to subtract that number, and it's going to become negative. And that totally makes sense because when you take a look at this vector that we're trying to find information about, the one that I'm going to be highlighting in pink, it has a positive x, it's to the right, and it has a negative y. Now, I think when I go forward to the next page where I reveal the x and y components, I don't know that I put negative there for the y. I know it's going to be down. When I find my x and y, these are the numbers I get. Are we still on board here? It's a long, arduous journey. That means unlikable. But what do we do with this? Well, what we do now is we say, we're back to almost the beginning when we first looked at vectors in 2 dimensions in Unit 1. If you know the x and y component of a vector, you just draw them tip to tail to find the answer to the question. So now what you need to do is either draw this. I prefer to draw this someplace else. Some of you don't need to draw it. I'm aware of that. You can just do the math by looking at what you've already drawn. In order for you to find the momentum, you're going to have to use the Pythagorean Theorem. I'll give you a minute to do that. I have, in all of my work here and all of my numbers, been mindful to keep all of my decimals. I've been storing things on my calculator before I've calculated things. So if you haven't, if you've been typing things away instead of scrolling up and re-grabbing them or storing them, your answer may be off a little bit, but remember, We learned from yesterday that the change in energy and therefore the change in the wavelength that the photon undergoes is very, very tiny. You don't want to round too much anywhere. So what is that? That is the momentum of the photon. And we can set that equal to h over lambda. Which means if we want the wavelength, we're going to have to take Planck's constant divided by the momentum. And we get 2.422 times 10 to the negative 10 meters, which is the answer we got yesterday. Now, let's put aside for a minute the fact that we're not getting the exact same answer that we got yesterday. Okay? I'll explain why we don't get the exact same answer in a bit. But when we used conservation of energy, which, I mean, think about what conservation of energy involved. Probably be easier for me to just write this. When we used conservation of energy, which was hc over lambda before equals hc over lambda afterwards plus 1/2 mv squared, we got the same VF, lambda VF, not VF, my mistake. We got the same final wavelength, right? Do me a favor and just for kicks, use this triangle and find this angle, which is not part of the question. I'm just asking you to find the angle. And this is just a trigonometric question. You can use sine, cosine, or tangent. It really doesn't matter. I'm going to go with cosine. I'm going to take the inverse cosine of the adjacent side divided by the hypotenuse step back and look at those numbers. (2.3866906) times 10 to the negative 25 divided by 2.7378213 times 10 to the negative 24. Making sure I'm in degrees. What just happened? And I get 85 degrees. And if you think I can just make up numbers so that happens, you can't. I could make up numbers, so I could make up a problem where we could use energy conservation to get a final wavelength. But if I just make the numbers up out of thin air, when you use a different method, you won't get the same answer. So this is all these things are very, very complicated, all of these equations put together. But does anybody have any questions with this entire procedure, or in particular the final couple of steps? When would you use conservation of momentum to solve this type of problem? I would say when you have no other choice. If you can use conservation of energy, why wouldn't you do that? Because all you have to do is find the two energies and subtract them to find the energy that's missing on the right-hand side. You don't have to deal with vectors. Even if you do have to apparently deal with vectors, there is a better method. And this is now at the bottom of the page that you're looking at. What Compton did is he took all of the math that we just did with the two-dimensional analysis, and he put it together with this idea of hc over lambda equals 1/2 mv squared plus hc over lambda. He put it all together using algebra and trigonometry and discovered that there's a relationship between Not the initial wavelength and the final wavelength, but the change in the wavelength, delta lambda, of the photon, and the angle at which the photon is scattered at. And this is the formula. If you take Planck's constant divided by the mass of the particle that's scattered, which is an electron, also divided by the speed of light, and multiply by 1 minus cosine of theta, where theta is the angle the photon is scattered at, you'll get how much the wavelength of the photon grows by. So think about this now for a second. If I asked you to find the final wavelength of the photon, we don't have to use conservation of energy. We don't have to use conservation of momentum. We know the initial wavelength of the photon, 0.24 times 10 to the negative 10 meters. We know the angle that the photon is scattered at, which I believe is 85 degrees. Am I right there? That's what was given in the question. So we can calculate delta lambda using h over mc times 1 minus cosine theta. And because this formula is a really wacky looking formula, I'm going to show my substitution here. It's not a formula that you're accustomed to in terms of the structure. You know, we don't normally have formulas where you have something times a binomial, basically, in physics. So delta lambda equals h, well, I guess I should write 6.63 times 10 to the negative 34. I'm not going to put the units in because it's just going to take up too much board space, over the mass of the electron times the speed of light, times 1 minus cosine 85 degrees. And there's no reason why you can't enter this all at once. But again, what I would always say to you is make sure you know how to use your calculator to find out what this is. So you cannot just be sitting there right now. You have to be calculating this. Okay. H is 6.63 multiplied by 10 to the negative 34 divided by the mass of the electron, which is 9.11 times 10 to the negative 31, also divided by the speed of light. You know me, I go divided by. If you want to divide by the product, you have to go divided by bracket and then type the mass of the electron times the speed of light, close brackets. I want to multiply that mess by, I don't even think I need a multiplication sign. You can put one if you like, 1 minus cosine of theta, which is 85 degrees. So I get for delta lambda 2.2 times 10 to the negative 12 meters. So I don't know why this, I think I know why this is, but what a lot of people will do now on an exam is to find the final wavelength. They will take the initial wavelength and subtract that number for some reason. And I'm glad that some of you are looking at me like, why would somebody do that? First of all, it doesn't make sense that you would subtract it to find the final wavelength because delta always means final minus initial. So if you solve for final, you're going to have that delta plus lambda 1 or lambda I. There's going to be a case in the next unit where it's not final minus initial. We don't do that. Okay. But it still is now. And the bottom line is you should know the wavelength is more afterwards because the energy is less. So all you have to do is take the initial wavelength plus the change in the wavelength. That would be 0.24 times 10 to the negative 10. That's meters, plus 2.2 times 10 to the negative 12. And you're going to get 2.422 times, I'm mistaken, it's 0.24 nanometers, isn't it, before? So it's either 0.24 times 10 to the negative 9, or it's 2.4 times 10 to the negative 10. But you are going to get the same answer we got using conservation of energy, which wasn't that hard on our brain, but it was a lot of work. And we got the same answer as we would using conservation of momentum. Clearly, this is very little work. You do one calculation to get the change in the wavelength, and you add it on to the initial wavelength. Why are these answers not exactly the same? Well, because Planck's constant is not exactly 6.63 times 10 to the negative 34. You know, if we use the exact values for any constants in any of our calculations and we redid them all, if we could somehow have infinite knowledge about nature's precise value of Planck's constant and the speed of light, we would get the exact same number. Algebraically, you can show that they're going to be the same thing, but numerically you can't. Any questions with that example? Yeah, go ahead, Ben. So for the delta lambda, can you check to see if you're in degree mode? Yeah. You are in degree mode? Yeah. Okay. So you're using an 84? Oh, I didn't put a bracket around 84. I think I saw what I did. You didn't put a bracket around where? Where the 3 times 10 to the 8 around the 1 minus. If you don't do that, then what you will be doing essentially is taking this and subtracting cos theta, which is not what we want to do. We want to take this hc over lambda and multiply by 1 minus cos theta. So this set of brackets here is critical. That'll fix it, I think. Any other questions with the work here in this example? All right. And number 4, I think this is our last example. Is that right? And then we'll be done for the day. X-rays of wavelength 0.28 nanometers are Compton scattered by free electrons. The X-rays are detected at an angle 78 degrees away from their original path. How fast are the electrons moving afterwards? Boy, you know what? This seems like there's no way I've given you enough information. But in order for you to find the speed of the scattered electrons, our primary goal becomes what's the kinetic energy of the scattered electrons. All right, so how would we do that? Well, if we could determine the energy of the photon before and determine the energy of the photon afterwards, then we could use conservation of energy to find the kinetic energy of the electron afterwards. Now, be very careful here. I'm not saying we should develop some big grand formula and do one calculation. That's not what I'm saying when I write this next part. This can be found using hc over lambda. This can be found using hc over lambda. And remember that this is our goal. That's what we want, right? So if we know those two photon energies, we can subtract them. We then have the kinetic energy of the electron, then we can find the speed. This is a deep question. It's not simple. I think it's simpler than conservation of momentum, which you couldn't even use in this question. Do we know the initial wavelength of the photon? Yes. So, I don't want to brush this aside. We'll do the calculation in a bit, but this is as good as determined. We know that because we know the wavelength. We can calculate it. Do we know the final wavelength? Are we told directly the final wavelength? No. But we can use delta lambda equals h over mc times 1 minus cos theta to find how much the wavelength goes up by, and then we will add that to the initial wavelength to find the final wavelength. So I'm going to kind of take a breather there with my explanation. We have the ability to find the final wavelength, just like the previous question. Okay, now ending the breather, if we know the final wavelength, then that will allow us to know the energy of the photon afterwards. Then we can subtract those two energies to find the energy of the electron, and then the rest of the problem is like stealing candy from a baby, because you just set that equal to 1/2 mv squared. So, oh, I got it right there. I don't know what this thing is. What is that? That's weird. So what I would like everybody to do is start by calculating the wavelength shift. I just want to check here how many of you are done and have an answer. Okay. So there's my calculation. Planck's constant divided by the mass of the electron, also divided by the speed of light, times 1 minus, this isn't 85, is it? No, it's 78. This is all garbage. Sorry. Guess I can just repeat this calculation. The only thing that changes, I think this is interesting. The wavelength shift is only determined mathematically by the angle at which the photon is scattered at. It's not determined by how quickly the electron moves at. It's not determined by the initial wavelength. It's not determined by any of that. So do you in fact get 1.92 times 10 to the negative 12? Excellent. So we get 1.92 times 10 to the negative 12 meters, which means that lambda f is going to be 0.28 times 10 to the negative 9 meters plus that 1.92 times 10 to the negative 12 meters. This will be the final wavelength. I got to get rid of all this garbage at the bottom of my screen. So lambda f is now known to us. .819 times 10 to the negative 10. I've told you this before in different contexts in this class and also Math 30. Sometimes your biggest, most important skill that you have to be on top of is being deliberate and organized and clear in your thought. You got a lot going on here. So maybe to help you organize this, I can make a little table. Lambda I is 2.8 times 10 to the negative 10 meters. Lambda f is 2.8192 or whatever it was times 10 to the negative 10 meters. You should be able to calculate the energy of each of these photons using E equals hc over lambda. So we have to find both of those energies so that we can subtract those energies so that we know the energy of the electron. This is what I mean by very careful, deliberate thought. Once you know the energy of the electron, you can find its speed. So this would be the next series of calculations. And, you know, before anybody asks, if you're thinking of asking the question, would we be given questions like this on an exam? The answer is yes. Okay. You wouldn't be given a whole exam full of these questions, but you might see it. I'm going to do hc over lambda for this one first because the number is right there. How many of you have an answer, by the way, now? A couple more people. Oh, that's hc divided by 2.81921531 times 10 to the negative 10. So the energy in joules of the photon afterwards is 7.055 times 10 to the negative 16 joules. The energy of the photon before would be hc over the wavelength before, which is 2.8 multiplied by 10 to the negative 10. So you get 7.1036. 7.1036 times 10 to the negative 16 joules. Again, you know, notice the slight change in energy. It's not a significant amount of energy. It's not like big. If you subtract these, the difference equals the energy lost by the photon, which is equal to the energy gained. This is conservation of energy by the electron. And we're almost done. How many of you now have an answer that you didn't a few minutes ago? A couple more. So now I'm going to subtract those two numbers. By the way, I don't know if it's occurred to any of you, but in case it has, you cannot subtract the wavelengths and do one energy calculation. It doesn't work that way. Minus 7.05515,465 times 10 to the negative 16 gives me 4.84 times 10 to the negative 18 joules. This is equal to the kinetic energy of the electron. So all we have to do then is multiply that energy by 2, divide by the mass of the electron, and take the square root. And now we find out if all of you that had the answer are getting the right answer, or maybe I'm not, but we're going to find out. I don't think I've done anything wrong here. I was very careful with this. I need to take the square root, and I get 3.26 times 10 to the 6 meters per second, which I'm seeing people nod, so that's the answer. As much work as that question is, if you didn't have that Compton scattering formula, delta lambda equals h over mc times 1 minus cos theta, at this level it would be impossible to do. You would have to do it with a system of equations involving conservation of momentum and conservation of energy. In other words, you would have to prove Compton's scattering formula in order for you to do it. You'd have to go through all the work he did for us to get that single formula that helps us. That's it. We still have one lesson to go in this unit. It's going to deal with what we've been talking about with Compton scattering is something called wave-particle duality. And there's another side to that wave-particle duality coin, and that's going to be called the de Broglie wavelength, which we will look at. I haven't decided if we're going to do our lab tomorrow or the next day. I have a couple of kinks that I got to work out of the setup for the lab in order for it to work well. And if I can get it done tonight, then we will have the lab tomorrow. If not, we'll do the de Broglie wavelength tomorrow and have the lab Thursday. Okay? And you know, when you get the lab turned into me and back for marks is not really going to be an issue with our exam, because I want to clear this up, because yesterday I told you a couple of things I noticed in my video. Your exam is Wednesday of next week. So between Wednesday of this week and Thursday of this week, we are finishing the unit and doing a lab. Friday, Monday, and Tuesday we are reviewing. We're reviewing 3 days, and our exam is Wednesday. Okay. Does anybody have any parting questions about any of the work we did here with this final example? I just have a parting comment, and it's that, you know, this is ultimately what you have to be doing here. You are going to be using conservation of energy. You then just have to find out all the missing pieces by going elsewhere, by looking at the Compton shift formula, which is the delta lambda formula, by looking at EK equals a half mv squared, E equals hc over lambda. There are some practice problems here, number 1 to 9 on page 59 of your unit handout. As usual, give me a minute or two to sort things out on my computer for the next class, and then I'll be around to help you out.